We're going to continue doing some more examples for Euler's method. Again, I consider it free and easy points, so it's definitely something that I want us to be able to work with because I think it's points we will definitely get come test time. So, given 3 times dy dx plus 5y squared equals sine of x, and y of 0.3 equals 5, and a step size of 0.3, find the value of y of 0.6 using Euler's method. And again, Euler's method is that the next y output is the previous y output plus the slope, dy dx, through the previous point. We will have an initial point of x naught, y naught, times a change in x. I'm going to make that just a little bit lighter. All right, so let's go about answering this question. There are some differences here, and this is why I use this example, because we're not out and out given dy dx. We're kind of given a implicit relationship, but we can definitely solve that for dy dx. So 3 times dy dx plus 5y squared equals the sine of x. We can solve that for dy dx. It's just some algebra steps up front. I'm going to subtract 5y squared from both sides, and I'm going to divide both sides by 3. I'm actually going to write that as 1/3 times the sine of x minus 5 times y squared. Since I'm going to be lazy and put the x part of it into my calculator, I'm going to go ahead and distribute that 3. All right, so I would put into y1, so at least it'll do that part of dy dx for me very quickly. So we can see if we start at the initial point, 0.35, there's x naught, y naught, that with a step size of 0.3 to approximate the value at 0.6 is 1 step, so that's wonderful. So y1 is y naught plus the slope through the previous point, which is 1/3 sine of the x value, x naught is 0.3, minus 5/3, the y value is 5. So there is dy dx through x naught, y naught, times a change in x. There we go. All right, and so whatever I get here will be the approximation using Euler's method for y of 0.6. So let's get our calculator. I have already put 1/3 the sine of x into y1, so I'm pulling up y1. I'm going to evaluate that at 0.3. I am subtracting from that 5/3 times 25. I can put it in there correctly. And then I'm multiplying that result by 0.3, and I'm adding to that result 5. And I get, if I put everything in there correctly, negative 7.470447. So negative 7.470. All right, so again, we may have to do some algebra steps up front to get where we need to be, but it's definitely something that we can do. I want to use this example to show you that we can use Euler's method even in the context of position, velocity, and acceleration, because remember, we are using the derivative function and an initial condition, x naught, y naught, to approximate y, or f of x, at some given value. All right, so if we have the derivative function, we can approximate the antiderivative starting with an initial condition using Euler's method. And we understand that velocity is the derivative of position. So the velocity in meters per second of a body is given as a function of time in seconds by v of t equals 200t squared minus t plus 2, where t is 0 or positive. The initial condition, x naught, y naught, here this would actually be t naught, x naught in that context using the correct notation. is the point 0, 2. T is 0 seconds. The position is 2 meters. Using Euler's method with a step size of 5 seconds, approximate the position at 10 seconds. So the change in t instead of the change in x is 5 seconds. So instead of saying y1, y2, y3, we're going to say x1, x2, x3. So let's see how many steps we need to take. We're starting at t equals 0. We're stopping at t equal 10. We have a step size of 5. So we're taking 2 steps. So we'll have x sub 1 that we're going to approximate, and then we'll have x sub 2 we're going to approximate, and that's actually going to be where t equals 10. So that will be the approximation that we're after. So I need the previous y output plus the slope through the previous point. And at the previous point, t is 0 times a change in t. And so this approximates to, that is 2 times 5 is 10 plus 2 is 12. So this is one where we actually may not have to have our calculator. So t sub 1, x sub 1 is now 5/12. See how easy that is? So with one more step, it's the previous output plus the slope through the previous point. Oh, this looks like it might get kind of interesting. Times a change in t. And now whatever that is our answer. But I want to show you something. If this was free response, we're done. Do not take the time, and it's valuable time you're wasting, where it's a timed test is what I'm trying to say. Don't clean that up. That is your answer. It's 12 plus the quantity 200 times 5 squared minus 5 plus 2, and that's times 5. And that's in meters. So there's the approximation at t equal 10 seconds. All right, so remember we can even do Euler's method in that context. So let's do another couple of examples. These are much more worded the way the actual AP questions will be worded. So I wanted to do a couple of examples like this. Consider the differential equation dy dx equals 1 minus y. Let y equals f of x be the particular solution to this differential equation with the initial condition 1, 0. F of 1 equals 0. Use Euler's method starting at x equal 1, that's x naught, with 2 steps. So it tells us the number of steps to take of equal size to approximate f of 0. Well, if we start at 1 and we want to approximate f of 0, this is pretty good because our steps have to be negative steps. Do you see that? And 2 steps going a distance of -1 means that our step size, our change in x, is -1/2. That's the only way we can take 2 steps starting at 1 and get to 0. Show the work that leads to your answer. All right, so y1 is the previous output plus the slope through the previous point times a change in x. Sorry, my mouth and my hand aren't communicating. I know that that previous point is 0. So this is 0 plus 1 times -1/2, so that's 1/2. I'm going to stop here, and I went from 1, took a step size in the -1/2 direction, and wound up with -1/2 being x1, y1. So here's my second step, and my y value, my previous y value is -1/2. The slope through the previous point times a step. And again, I don't have to clean that up, not one tiny little bit. I am, because I have another step size of negative, hang on just a second, I did it again, didn't I? My step size is negative 1/2, but from 1 taking negative 1/2, that leaves me at positive 1/2. And I'm sorry I wasn't paying closer attention to that, but I knew that my derivative was simply based on the y value, so that's what I was paying attention to. So none of this is incorrect. That's actually fine. So one more step size from positive 1/2, one more step size in the negative 1/2 direction leaves me at f of 0. So that is approximately negative 1/2 plus 1, and I could say plus the quantity 1/2. I'm probably confident in that. And there's my answer. So don't ever simplify if you don't have to. If we're going to make a mistake, this is where we're going to make it. We're going to try to clean it up because we've been, it's just been pounded in our brains that we have to simplify every answer, and we don't. So please make sure you don't lose a point that you've already earned by simple algebra. So finally, consider the differential equation dy dx equals 6x squared minus x squared y. Let y equals f of x be a particular solution to this differential equation with the initial condition negative 1, 2. So they look a lot alike. Use Euler's method with 2 steps of equal size starting at x equal negative 1 to approximate f of 0. So now our change in x is going to be a positive 1/2 because we're taking 2 equal steps. We're starting at negative 1. We're headed to 0. That's in the positive x direction. So we'll have y1, we'll have y2. We can show them that we realize that y2 will be the approximation for the output of the function at x equals 0. So I need the previous y output plus the slope through the previous point minus negative 1 squared, and my y value is 2, times a change in x. So 6 times 1, that's 6, minus 1 times 2, so that's a 4, times 1/2. So this is 2 plus 2, that's 4, if I did all that correctly. So now I am at the point negative, let's see, I was at negative 1. I went in the positive direction 1/2. So now my new x value is negative 1/2, and my new y value is 4. And so it's the previous y output plus the slope through the previous point, negative 1/2 squared times y times a change in x. And there we are. There's our answer. Okay, so we got all that done in one video. You're welcome. And so come to class next time and we'll work some AP Euler's method problems.